Hello, I'm Yoonseon Choi from Hanyang University, and I'm glad to present our paper, Early Prediction of Cybersickness in Virtual Reality using a large language model for multimodal time series data. This work was done with Dayoung Jeong, Bogoan Kim, and Professor Kyungsik. Before I begin my paper presentation, I'll briefly introduce the research background which focuses on predicting cybersickness. Recently, VR applications are expanding in fields like education, healthcare, and entertainment. But cybersickness, which refers to symptoms such as nausea or dizziness during VR experiences, can disrupt user immersion and the usability of VR. To measure cybersickness, sensor data measured in electroencephalography devices or head-mounted displays are usually used. However, EEG measurements are somewhat intrusive, so the data collected in such environments may lack reliability and generalizability. Therefore, we aim to predict cybersickness using only multimodal sensor data, including eye and head movement collected from HMDs. Existing cybersickness prediction models have some limitations despite showing good performance. These models predicted at a single point in time using point-wise multimodal sensor data at the current moment. If these models are integrated into VR content, this approach only allows for mitigation measures after the user experiences cybersickness. For a more natural VR experience, it is necessary to predict it at the future time steps based on HMD sensor data measured over time. Large language models are effective for time series forecasting. They can identify hidden trends and seasonality in time series data based on pre-trained domain knowledge. And their ability to understand the context of time series data helps improve prediction performance. Therefore, we propose a model for early prediction cybersickness based on time LLM, which employs a pre-trained LLM for long-term time series forecasting. This is the overall framework of time LLM. It takes input data of length L and predicts data of length T. To predict cybersickness, we use Fast Motion Sickness Scale, FMS. We also use the GPT-2 as a pre-trained LLM. Let me explain the structure of the model in detail. First, to embed the input data, instance normalization is performed by decomposing multivariate data into univariate to preserve the characteristics of each data feature. Each univariate data is divided into patches of a certain length. Patches can preserve the locality of the time series data, making it easier to capture patterns. Next, patch reprogramming is an embedding process that aligns the patches and word embeddings from the pre-trained LLM. We can select the word embeddings related to the characteristics of time series data by linearly proving. Then, we can obtain the text prototypes by combining selected word embeddings such as show up then down steadily or no fluctuation stable state. We can get reprogrammed patches, which are referred to embedded multimodal sensor data through multi-head cross-attention with patches and text prototypes. We also use the prompt to describe key information about the input data. The prompt helps the model understand embedded multimodal sensor data. The prompt is vectorized by the pre-trained LLM embedder and prepended to the reprogrammed patches. This embedded prompt is referred to as a prompt as prefix. Look at the example of the prompt as prefix. The prompt includes the overall dataset context, task instruction which is a specific guideline of forecasting, and simple input statistics. Finally, the packed vector is embedded into pre-trained LLM. Then the model predicts the FMS of the future steps. We use the RMSE VR open dataset for our experiments, which is collected by 45 participants using HMDs. Then the RMSE VR dataset was split into 3 parts for each 45-second video. We set the length of input to 25 and output to 20. We selected some baseline LTSF models, D-linear, transformer, and patch TST. Additionally, we conducted ablation studies by removing key models. Time LLM showed comparable performance in the cybersickness domain based on other baseline models, and it demonstrates effectiveness of reprogrammed patches and prompt as prefix. These results suggest that the use of pre-trained LLMs for multimodal sensor data can be effective for integrated analysis and training of modalities. Nevertheless, we acknowledge two important limitations. First, time LLM has an excessive number of parameters due to the use of LLMs, which results in long training times. To address this, we aim to optimize the patch reprogramming model. We expect to reduce the number of parameters by refining linear proving method to better extract relevant word embedding to multimodal sensor data. Second, this model is still room for enhancement of prediction performance by improving the existing prompt. To address this, we will try to embed detailed descriptions into the prompt through feature extraction, and we aim to enhance the interpretability of the modalities. We proposed time LLM-based model for early prediction of cybersickness using multimodal sensor data. In conclusion, cybersickness can be early predicted using only the multimodal sensor data collected from HNDIS and an LLM-based LTSF model. In addition, we confirmed the effectiveness each model of time LLM. We hope to provide valuable insights into the field of cybersickness prediction modeling. For more details, please refer to our paper. Thank you for listening to my presentation.